Let's take a look at the situation that's outlined in the Tipper's book, pages 178 through 180. All three of these pages deal with the same situation. Frictionless inclined planes, block A, block B, sliding down. Both start at the same height, both end at the same height, but one of them takes a steeper path. A is a much steeper incline, B is a more gradual incline. Student A on page 178. I think the normal force doesn't do any work on either block. You agree with that part of the statement? I agree with that. The normal force does no work. The normal force is always perpendicular to the direction of motion. If the normal force is that way and the direction of motion is that way, they are 90 degrees apart. So the work done is the normal force times the displacement times the cosine of 90 degrees. The normal force does no work. This is always true when we have sliding objects like this. The only time the normal force does work on an object is if the normal force is in the direction of motion. So let's say I have an elevator going up, and I've got a box sitting in the elevator, and the whole thing is going up. Let's take a look at that box. There's a normal force up on the box from the floor of the elevator. There's the weight of gravity down. And as this box moves up, the normal force is doing work. It's pushing the box in the direction of motion. It's doing positive work on the box. So don't get in the habit of saying normal force never does any work. It has to be in the direction of motion. When boxes are sliding on inclined planes, the normal force does no work because it's perpendicular to the direction of motion. So far, student A has this down pretty well. The normal force doesn't do any work on either block. The force on the block by the ramp is perpendicular to the ramp. That's correct. The normal force is perpendicular to the ramp. And the displacement is parallel to the ramp. So the dot product is 0. So student A not only has the correct answer, their logic seems right on. If you're confused by the dot product term, don't worry about that. That's the mathematical way of writing what I already wrote here. The work done is force dot product with the vector displacement. And a dot product between two vectors yields a scalar. Work is a scalar quantity. And how do we figure out the dot product? It's the magnitude of that first vector multiplied by the magnitude of the second vector multiplied by the cosine of the angle between them when we put their tails together. Student B, let's take a look at what student B is saying. Work is force times displacement. Okay, in the simplest case, that's true if the force is constant and in the same direction as the displacement. Yeah, I'd buy that. The work done on block A is negative, while the work done on block B is positive, because the displacement for B is in the positive direction, while the displacement for A is in the negative direction. I think what they're trying to say, it's a little confusing because we have ramps and motion in 2 dimensions here. I think what they're trying to say is that they've chosen to the right as positive, and block B is basically going to the right. It's also going down, but it's basically going to the right. And block A is basically going to the left. It's going down also. But let's ignore the vertical motion. Let's just look at the horizontal motion. Because block B is going in the positive direction, they felt that positive work was done. Block A going in the negative direction, negative work had to be done. Let's take a closer look at this. Let's say block B is going to be moving in this direction, and we're applying a force on it. What do we get for the work done on block B? It's the force, the magnitude of the force, the magnitude of the displacement, and the cosine of the angle between them. And since the force and the displacement are both pointing in the same direction, both pointing in the positive direction in this case, then the angle between them is 0 degrees, and we just get force times delta x. Now let's look at block A. If block A was being displaced in the negative direction by a force in the negative direction, the work done is equal to the force times the displacement times the cosine of the angle between them. And these also have a 0-degree angle between them because they're pointing in the same direction. Work done is independent of your choice of coordinate system. It only depends on the relative orientation of the force and the displacement. Okay, so student B is thinking that work somehow, the sign of the work done somehow depends on the choice of your coordinate system. It does not. The work done on both of these blocks by the force of gravity is going to be positive because the force of gravity is basically in the same direction these blocks are moving. It's doing positive work on the blocks. It's increasing the block's speed. It's increasing the block's energy. Student C, since work is force times distance, again, in the simplest case, when force is constant and in the direction of the distance, that's true. And the distance that block B travels is greater than block A, the work done is greater for block B. So they started out pretty well, but they got off on the wrong track. The distance block B travels is greater, but the force in that direction is smaller. Work is this product of force and distance if they're both in the same direction and the force is constant. So for block A, the force down the hill, I'll call that force of gravity parallel, is just mg sine theta. Right? Let's draw a free body diagram for block A. We had a normal force, no friction force in this case. We had the weight, I'm going to call that F sub g, force of gravity. We can break that up into a component that's perpendicular to the incline. And what's that going to be equal to? mg cosine theta, where that becomes theta. And there's a component in this direction parallel to the surface, mg sine theta. So the force in the direction of our motion is mg sine theta. So the work done on A is going to be the force in the direction of motion multiplied by the distance, and the work done on B is going to be similar. But let's take a look at this. The work done on A we know is going to be equal to the work done on B, and the work done on A is its force, which is big, times its distance, which is small. And the work done on B is its force, which is much smaller because the incline is not as steep, multiplied by its distance, which is big. Hopefully you're getting a visual here. Big force times small distance can be equal to a small force times a big distance. So student C has half the equation right. The distances are different. What they forgot is that, whoa, the component of gravity that's pointing down the hill is bigger in case A than it is in case B. All right, let's continue on page 179. Same situation. Student A, work is the dot product of force and displacement. We've talked about that. I'm good with that. And the weight is the same since the blocks are identical. Okay, so far so good. But block B travels further, so more work is done on block B by the gravitational force than block A. Okay, we've just talked about this, but let's look at it a different way. In the previous example, I said, let's look at this component. Let's look at the component of the gravitational force that points down the incline. and then take the distance along the incline. But there's another way we could have looked at it. We could have said both of these blocks go the same distance straight down, vertically. And both of them have the same force of gravity straight down. So in going from their initial height to their final height, the same work was done. The distance was the same, the force was the same, and so they end up with the same amount of work done. And the reason we can do this is because gravity is a conservative force. And we know that for conservative forces, the work done between any 2 points is the same regardless of the path. If A takes a short path, we could take a different path going straight down and then across. I'll call that path C. So path C and path A have to have the same amount of work done. And obviously, there's no work done by the force of gravity in the second leg of path C, only in the first leg. Straight down, the distance multiplied by the force of gravity gives you the work done by gravity. Student B, both blocks fall the same vertical distance, so the work done is the same. Yes, we just talked about that. Yes, that's another way of looking at it. Just look at the vertical distance when you're talking about gravity, because these horizontal components, the work done by gravity over those sections is 0. And gravity is a conservative force, so we can take any path to get from our starting point to our ending point and find the work done. Student C, by Newton's third law, the force exerted on the block by the earth is exactly canceled by the force exerted on the earth by the block, so the work done is 0. The earth and the block are a Newton's pair, Newton's third law pair, and they do exert equal and opposite forces on each other. But when we are interested in the work done on the block by the force of gravity, we don't really care about what's happening to the earth. All we care about is the force acting on the block and the distance it's moving through. So the work is force times distance times cosine of the angle between them. It doesn't matter what's happening with the earth. There's a force on our block. The block is moving. The force is acting on that block as it moves through a distance, delta x. And so there's work being done on the block. And student D says, the dot product depends on the angle that the force makes with the displacement. If we put the displacement and the force vectors tail to tail, the angle is smaller for block B than for block A. So the work done is greater. Okay, so again, this is just like the previous page where the person said the distances were different. They forgot that the forces were also going to be different. In this case, what they're saying is the work done is the force times the displacement times the cosine of the angle between them. And the cosine of the angle between them is going to be different. But what they're forgetting is the distance is also different. And when you put everything together, what you end up with is the fact that the work done on box A by gravity is equal to the work done on box B by gravity. So if we take the force as being straight down, mg, and we take the displacement to be, for B to be delta xb, then what do we end up with for the work done on B? The force, the displacement, and the cosine of the angle between them, which is actually this angle here. So that would be what, 90 minus theta b. And for block A, the same force, it's an identical block. Delta XA, which is much smaller, and the cosine of 90 minus theta A. So the student here is right. Those cosines are different. What they're forgetting is the distance is also different. When the cosine increases, as that gets bigger, this gets smaller, and the work done by A is equal to the work done by B. Page 180, same situation. The first question, from the starting height to the final height, the work done on block A by the normal force is 0. We've discussed that one already. From the starting height to the final height, the work done on block A by the gravitational force, is it positive, negative, or 0? Positive, because the object is going down and the force of gravity has a component in that direction. So they're in the same direction. We get a cosine 0 degrees there. We get a positive value for the work done. Basically, the force of gravity, when it has some component in the direction of motion, it would cause the object to speed up. If nothing else, no other force was acting on the object. Then it's doing positive work. If it causes the object to speed up, it's doing positive work. This is certainly doing that. From the starting height to the final height, the work done on block A by the gravitational force is equal to the work done on block B by the gravitational force. We've been through a few different ways of thinking about that. Number 4, the speed of the block. Block A, as it crosses the lower dashed line, is equal to the speed of block B, because the same amount of work has been done on both blocks. And we know from our work kinetic energy theorem that the change in kinetic energy is equal to the net work done on our object. So both of them change in kinetic energy by the same amount. And what is kinetic energy? 1/2 mv squared. So that's the delta K. Delta is always final minus initial. These two blocks, A and B, are identical, so they have the same mass. They must have the same velocity. And number 5, block A will cross the lower dashed line before block B. Because block A has a greater acceleration, the component of the gravitational force down the incline is more for block A than it is for block B. And it's going a shorter distance, so it has a larger acceleration and a shorter distance. It's going to get there in less time.